like to talk about today is a different point of view on the NGSS. When somebody talks about this talk, we assumed that most people in the audience would be curriculum developers, faculty members, science education faculty, that kind of thing. And those kind of people definitely have a certain point of view. Maybe even scientists, right, have a point of view on the next-gen standards. But what does it look like when a cognitive scientist takes a look at them? And I was really interested in what Kim was saying, because in order to come up with our thoughts on this, we actually had to create an externalized model of what's happened to the next-gen standards over time. So we started with the frameworks, and we tracked every different draft, including the April 9th, the May 3rd, the May 15th, and the June something versions of the final NGSS. And I just had to show you pictures of that at the end. But when we look at them, I think we look at the NGSS differently than you guys do. In particular, we're looking at the ways in which students can go about learning content and the ways in which they process it. And in truth, every single one of these things is probably worth its on top, but it can't be. So we're only going to do 4 in today. And I would say that all 4 of these are things that most people generally would describe as being a misconception. However, from a cognitive science point of view, we found that big umbrella of misconceptions has been really unfruitful in terms of being able to actually act on it and improve student learning. So instead, we've taken misconceptions and broken it down into different parts. For instance, but we do still have misconceptions, all right? So we have misconceptions which we think of as just bad data. It just means a kid has got something in their head that just ain't so, right? And so when we look at the NGSS, we're looking for those kinds of statements in the standards that are not going to help a student overcome those misconceptions, but are probably going to actually reinforce them. And you'd think we wouldn't find any, but we did. So if we take this one, for instance, it says the locations of mountain ranges and ocean trenches and ocean floor structures, earthquakes and volcanoes occur in patterns. Yeah. Most earthquakes and volcanoes occur in bands that are often along the boundaries between continents and oceans. So the problem with this, from a cognitive science point of view, is that many students have a misconception that continents and plates are the exact same thing. So when we tell them that these things occur along the boundaries between continents and oceans, that is going to stick with them because it's what they already believe anyway. And when you come back later on and try to correct what you said by saying that it's really plate boundaries, you're not going to be very successful, which is why we continue to see this kind of misconception even in students who've taken earth science and platonics several times. And of course, one would question whether it's even scientifically accurate. So when we look at the face of the planet Earth, I think, if we went through and counted all the dots and the triangles, we'd probably find out that most earthquakes and volcanoes do not occur where the continents and oceans meet, and New Jersey is really happy about that, I'm sure. But they occur in the ocean, right? Which brings us to the second problematic statement in this, from a cognitive science point of view, which is that major mountain chains form inside continents or near their edges, which would seem to be entirely comprehensive and cover everything. But what we know is that when students think about geology, they rarely think about anything other than land. And of course, our Earth is 70% not land. And again, if we look at this picture that all of us have seen, indeed, the Earth's major mountain chains are not on land at all, but they're in the ocean. So when I look at that standard from a cognitive science point of view, what I see are 2 things that are actually going to reinforce student misconceptions. So what do we do about that? Well, it's going to require those of us who are writing curriculum and those of us who are putting courses together to be hyper aware of those kinds of common misconceptions that students have. And we need to explicitly address them. So for instance, if you're using that standard in a piece of curriculum you're writing, you probably need to put in a little extra statement that says, well, we know it says this, but really maybe a more accurate way of saying it would be this. We're going to need to explicitly confront it. And we need to definitely remember that not everything that every kid gets wrong is a misconception that can be corrected by just telling them that they're wrong, or even by using conceptual change models. So another thing that we look for is the capacity for the NGSS to build knowledge over time. So I bet if you guys look at this screen, every one of you can find a piece of content that you teach in your course. All the earth science is represented up there. And we know that even at the college level, students really struggle with this. Well, what do they all have in common? Is that they all rely upon students' understanding of Newton's third laws. Inertia, force, mass, acceleration, paired forces, balancing. And we know that from work by Hake and others, that even students who have got a college degree in physics frequently don't really understand Newton's laws. So why is that? Well, Newton's laws, it turns out, require you to understand friction. If you don't understand friction, you can't understand Newton's laws because the world doesn't perceivably act under Newton's laws. So you've got to be able to filter the friction out of the system, right? We knew that when we put together the original frameworks, the National Research Council framework for K-12 education. And so it was front-loaded in the physical sciences with 7 separate standards related to friction, all in a K-2, mostly in a K-2 tubing, which is a great cognitive time to have kids working on that. Because every little kid knows that it's easier to roll a car across a linoleum floor than against a carpeted floor, right? It is a perfect opportunity to have kids learn that scientific content. Unfortunately, it was removed. Every single reference to friction was removed from the next-gen standards. It no longer appears except in a sentence where it says, don't mention friction. What that means is that we are setting up students to not be able to learn Newton's laws, which means they're not going to be able to understand your earth science content. So what do? I'm not going to tell you, because there's another thing that we might look at. And that is students' abilities in our geoscience classes to understand things that rely upon chemical bonds, which, as it turns out, we think is probably highly related to spatial reasoning. Right? All of those things, all those chemical reactions, require a student to understand the atomic molecular theory. And fortunately, we have really, really great research on how students can get there. But what the research tells us is that to understand the atoms, students really need to be able to understand density. And to understand density, they really, really have to understand measurement, which was really, to me, a shocking, core belief-altering kind of finding that Smith and her colleagues were able to come up with. Really great research. Knowing this, we built into the frameworks explicit instruction in students making measurements of lots and lots and lots of stuff between kindergarten and second grade. As you can imagine, of course, that is also one of the pieces of the frameworks that was removed. So we are now poised students to not be able to learn Newton's laws and not be able to understand the atom. So what do? When moments like these, we fall back on what the NRC has said, which is, in construction of curriculum, please refer back to the frameworks, because those had a lot, it was a more complete package. There have been lots and lots of people to work on the framework and the NGSS over time, and those groups of people have changed. So most of the cognitive scientists were involved in the construction of the framework, but not so much on the final stages. So to get that cognitive science research piece back in, we've got to go back to the framework and reinsert that content. If you're writing curriculum for K-2, please have them measuring things. Because if you don't, they're not going to be able to understand the atom, and they're not going to be able to understand climate change. Oh, and of course, for 10 in the back there, when you're teaching a spatial concept, you've got to use spatial instructional techniques. The last thing I want to talk about was issues of identity and belief. And what we found is that this misconception that we think people have is not really a misconception at all. It's a willful resistance to believe what you told them. When it comes to climate change, Big Bang, evolution, climate change, what we know is that the facts don't matter. There's absolutely no point in using a traditional conceptual change model with students on these issues. They simply do not want to believe it, and it's way too threatening. So in order to combat this in the frameworks, we originally put in a whole bunch of climate change and evolution, and not so much Big Bang, starting at the kindergarten level and building. Lots of experiences when you're really young dealing with both evolution and climate change. And in the middle school level, hit the Big Bang really hard. Unfortunately, as you can imagine, most of that material has now been removed. In fact, the Big Bang does not occur at all anywhere in the NGSS. There's no description of the Big Bang as the beginning of the universe. There's no age for the universe. There's no idea that the universe started with a large expansion. It's gone. All that remains is a list of some of the evidence that we have for the Big Bang at the high school level, which, of course, as we know, it is a huge, huge problem to get earth science taught at the high school level. Most students do not take it. So if something has been left to high school within the earth sciences, most students are never going to see it. So what do we do? Well, we go renegade and we reinsert the content into the framework. You have to teach it early, teach it often, and more than that, you have to teach it using a hot conceptual change model, which is very different than regular conceptual change. In a hot conceptual change model, this is very much like what you were describing before with the energy curriculum. Having students look at refutational texts, having them look at a situation and talk about it in a way where the emotions are kept low so that they don't feel threat. We now know that that works pretty well with Big Bang, evolution, and what's their own climate change. It does actually work. So I think that's all I have time for. That was 13 minutes, and I'm gonna clear the floor. Let's see if there's any questions.